Hello students, welcome back. Today we'll continue with the seventh video lecture of chapter number 9, Ray Optics and Optical Instruments. Okay, I hope you have watched all my previous videos. If you like my video, then please subscribe this channel. Okay, so today's topic is total internal reflection. Okay, so it's total internal reflection. Okay, you had already studied the basics of this topic in standard 10. Okay, now let's start with this topic. Now, if you take any medium, okay, if you take any medium, if its refractive index is higher, that means its optical density is higher. Means you can say that higher the refractive index of material, higher the optical density. And remember, this optical density is independent of the density of the material, means independent of the mass and independent of the volume of the material, right? So density and optical density both are different terms, right? If a material is having higher density, that means compared to its volume, its mass is higher, right? You are using the symbol density is equal to mass by volume. So for the same amount of volume, higher the mass, higher the density, right? But this is not that. It is optical density. Means if I say that a material is having high optical density, that means that it is having higher refractive index. Okay. So now, when a ray of light pass from optically rarer medium to optically denser medium, okay, or from medium having low refractive index to high refractive index. Here, this is the medium. I will write down low refractive index. And let's say this is the medium, or let's say this is filled with water. Okay, this is air, this is water, that is high refractive index. Okay, so when a ray of light passes from low refractive index to high refractive index, what will happen? Or when a ray of light passes from one medium to another medium, okay, one medium air to water or water to air, what will happen? A part of it is refracted here, but a smaller portion is also reflected. Clear? So when a ray of light incident on the surface of water from air, okay, what will happen? A part of it is refracted and a part of it is reflected. Remember, the intensity of the reflected ray is quite small. It's very small compared to that of refracted ray. Clear? Okay, and it also depends on the medium, that how much is the intensity of this reflected ray. Clear? But in normal case, when a ray of light passes from air to water, the intensity of reflected ray is lesser compared to that of water, refracted ray. Okay, so now see, if I zero is the intensity of incident ray, clear, and I is the intensity of reflected ray. See, I'm not talking about this refracted ray. I'm talking about this reflected ray. Okay, that is intensity of reflected ray. Then I will be equal to n2 minus n1 upon n2 plus n1 whole square into I0. Clear? Where what is N2? N2 is the refractive index of water, or you can say higher refractive index, and N1 is the refractive index of the air, that is lower refractive index. Okay, you can take any value of N2 and N1. You can also change it. You can take this value of N2 and this as N1. Then also do it because here it's square. So it's negative, then it will come positive. So I is equal to N2 minus N1 upon N2 plus N1 whole square into I0. Clear? So now what is the refractive index of water here? For water, N2 is equal to 1.33, right? And for air, N2 is equal to 1. Now, if I take this as a glass, then the refractive index will be 1.5, right? Instead of water, if I take this as a glass, right? Then what will be your answer? I will be equal to 1.5 minus 1, 0.5, and whole square, right? That will be 0.25. Clear? 1.5 minus 1, that is 0.5 whole square. And here 1.5 plus 1, that is 2.5. So it will be 6.25. Okay? So this will be equal to, I can write it down as 25 upon 625 I0. Clear? So that will be equal to, sorry, I is equal to 25 upon 625 I0. So this will be equal to 1 by 25, that is 0.04. So converting into percentage, I will be equal to 4% of I0. For percentage, I need to multiply it by 100. So it is 4% of I0. Okay. So this was just a calculation. Okay. You need not show this calculation where if it is asked in the exam. You can directly write down that putting the value of N2 as 1.5 and N1 as 1, I will get the intensity as 4%. The intensity of reflected ray is 4% of the intensity of incident ray. Means the intensity is only 4% of reflected ray. Means that is very, very less. Clear? I'm repeating once again. See, higher the refractive index, that means higher its optical density. When a ray of light enter from one medium to another medium, one medium to another transparent medium, I would say, then a part of the ray is refracted and a part of it is reflected. Okay, as shown here. So if I0 is the intensity of incident ray and I is the intensity of reflected ray, then according to this formula, I will be equal to N2 minus N1 upon N2 plus N1 whole square I0. So if I take this medium as air and this as glass, then the reflected ray will have intensity of 4% of incident ray. Okay, so just note down this. See, total inner reflection, the topic is still remaining, we'll continue, but till then, just note down this topic. Okay, now let's continue this topic further. Okay, now many times you might have observed that when you're observing from some angle, the surface of the water will be very bright, right? You might have observed in swimming pool or anywhere else that sometimes the surface of the water that is very bright, it's shining, right? So why does this happen? Okay, this happens because what happens when the light rays enter from air into the water. Okay, after striking at the bottom, it is reflected. Now, when this reflected ray, when it tries to enter from water to air, at that time, this reflected ray is reflected on the surface. So, at that time, the surface of water appears bright. Okay, let's take example. Okay, I am taking an example. Let's take this is a tank filled with water. Okay, let's take here a source of light S. In normal case, what happened? Light is incident on this way, reflected, when it comes reflected, and then it's on surface. So how does this happen? See now, let's take that if a source of light is inside the water. So this is emitting the rays, light rays. So let's take first example. The ray which is coming in this way, exactly 90 degree. Okay, means it's in the direction of normal. It will be in the same direction. Okay. Now at this place, let's take this as point B. Now at point B1, this is the sorry, this is the incident ray. Now this is the normal. Clear? This is incident ray theta. Okay, I will write down theta 1. What will happen? Here N2, let's take this as N1, means refractive index of liquid, and N2, this is air. So what will happen? The ray of light is entering from optically denser to optically rarer medium. So it will bend away from normal. So let's take this will be the reflected ray. Clear? Now let's take one ray in this direction, moving away. This point B2. This is the normal theta 1. Now in this case, you will say that angle of incident is higher compared to this. So angle of reflection will be also higher compared to this, right? So it will bend more. You can see this is higher. Clear? Now what will happen when the ray of light enters from one medium to here, refracted ray, and it is also partially reflected. Same way it is also partially reflected. Remember intensity I n2 minus n1 upon n2 plus n1 whole square into I0. That will be the intensity. Now if I again extend this angle, at what will happen? As you will move, the refracted ray will bend towards surface. So at one angle, the reflected ray is on the surface. This theta 1 equal to C, and the refracted angle is equal to 90 degree. Right? What you observed initially, the refracted angle was this. As you increase the angle of incident, it bends towards surface or away from normal, and at one stage, it will be parallel to the surface. So this angle is 90 degree. This angle of incident is called critical angle. Okay, so now what is critical angle? This is the angle of incident when the angle of refraction is 90 degree. That is critical angle. What is this? It is the angle of incidence when the angle of refraction is zero. Okay, but remember it can only occur when the ray of light enters from optically denser medium to optically rarer medium. Okay, clear? So now see what happened. Now if I will increase again, then what will happen? This angle of incident is higher than angle of than critical angle. So now it will be reflected internally. Now when it reflects internally, then it follows law of reflection. That means in this case theta 1 will be equal to theta 2, right? So this we will say it as total internal reflection. Clear? Now in this case, there is no refracted ray. Means the total intensity will be in the reflected ray. And this will obey the laws of reflection. That is theta 1 angle of incidence equal to theta 2 angle of reflection. Clear? So now remember the important thing, the angle at which, the angle of incidence at which the angle of refraction is 90 degree is called critical angle. We will name it as C. Okay, so let's name this as point B3, this as B4. So at B3, applying Snell's law, at B3, what is the result? N1 sine theta 1 equal to N2 sine theta 2. Clear? So now what is N1? That is the refractive index of that. Let's take this N1 equal to N and N2 equal to 1. This will be L. So this now becomes, okay, let me write down here N1 equal to N and N2, that is refractive index of air, that is 1. So N sine. What is theta 1? At this place, it's C, critical angle. So N1 sine C, that will be equal to what is N2? 1. What is theta 2? 90 degree sine 90. So the value of sine 90 is 1. That means n sine c equal to 1. That implies sine c is equal to 1 by n or c equal to sine inverse 1 by n. Clear? So this is critical angle. So if you are asked to find out the critical angle, then just take this formula 1 upon refractive index. That means the reciprocal of refractive index. Sine C will be equal to reciprocal of refractive index. Now using the sine table, just find out the value of C. Clear? So I'm repeating this topic once again. See what we have taken. We have taken a medium of water, right? And this medium is air. We are assumed let S be the source of light inside the liquid or inside the water. So the ray passing through B will be in the same direction as it is in the direction of normal. Remember, whenever a ray enters from one medium to another, perpendicular to the surface, it will not deviate its direction from its direction. It will remain in the same direction. When it comes from B1, okay, it will bend away from normal. Increasing the angle of incidence increases the angle of refraction. At one stage, at theta 1 equal to C, the angle of refraction will be 90 degree. This angle is called critical angle. The angle of incidence at which the angle of refraction is 90 degree. Okay? And if we still go on increase the angle, then it will follow, it will be totally reflected internally. So this is total internal reflection, and it will follow law of reflection. Okay, so now taking Snell's law at point B3, n1 sine theta 1 equal to n2 sine theta 2, n1 the value is n, we are taking value of n, n2 it's air, so we have taken 1. Theta 1, angle of incidence C, angle of refraction 90 degree. So putting this, we get sine C is equal to 1 by n, or C equal to sine inverse 1 by n. Okay, so to find out critical angle, take the formula sine C is equal to reciprocal of the refractive index. Sometimes critical angle may be given. Okay, and you have to find out the refractive index. Like if the critical angle is 30 degree, then sine 30 will be equal to 1 by 2, right? So n will be equal to 2. So the refractive index of the medium will be equal to 2 with respect to air. Okay, now if these both are different medium, if these both are different medium, then this will be equal to n2 by n1, means n1 upon n2. Sin C will be equal to n1 by n2. Sorry, my mistake. Sin C will be n2 by n1. Okay, in numerator, the outside medium, this air, and denominator, the refractive index of the medium where there is source. Okay, so just note down this topic. Okay, students, so that's it for today. In our next video lecture, eighth video lecture, we will study about the uses of total internal reflection. Okay, so that's it for today. Thank you.